day everybody. My name is Dr. Chris Hansen and today we're going to find out about the sun's supergranules and how we can see them with sound waves. Let's begin. Here is the sun. Now you might be wondering why it looks so different from how you see it every day. But these images are produced by NASA's Solar Dynamics Observatory and is generated every 45 seconds in glorious 4K by 4K resolution. Zooming in, we see a pattern of fine black and white structures. These are known as granules, roughly 1,000 kilometers in size, and they live for around 10 minutes and are very shallow in the sun. The sun is generating a lot of heat, and in the outer 30% of the interior, this heat is transported through a process known as convection. Hot material rises to the surface, cools, and descends. The white parts in these granules are hot material coming up, and the black is the cold material sinking. These granules are the smallest scale of convection in the sun, but convection also occurs on much bigger sizes. Now it's not obvious right away, but these granules are slowly being pushed horizontally by larger flows underneath. We call this advection. In the short lifetime of the granules, they are being pushed around the image by very slowly moving supergranules that lie underneath. If we track the motions of the granules for a day, we can measure the surface profiles of the supergranules. And this is what we see here, a field of supergranular flows. Supergranules are roughly 35,000 kilometers in size. That's almost 3 times wider than the Earth. And similar to granules, are a result of hot material rising to the surface to cool. But in this time, the material is coming from much deeper inside the sun. The red features are outflows of hot material, and the blue ones are inflows, where cold material gathers before descending back down into the interior. The difficulty for scientists is how to see below the surface. We cannot use light since the surface is optically thick, so we have to rely on sound waves. More on how we do that in a second. But the interaction between sound waves and the supergranules is very weak, so first we must improve our signal by averaging. We identify all the locations of the supergranular outflows and shift all the data to the center of the image. In doing so, we have built the average supergranular flow. Now, while we can't see below the surface, the sun is full of sound waves. These sound waves are generated by the small granules shown at the beginning, and they propagate throughout the near surface layers of the sun. If we observe a single wave source, the wave starts and travels through the plasma and eventually interacts with the average supergranule. The wave then either speeds up or slows down. But there are waves everywhere in the sun, going in all directions and different paths. By measuring how all these waves change, we start to get a picture of what the supergranule looks like below the surface. Let's take a slice through this supergranule and see what the waves are telling us. So here we are. The reds and the yellows tell us about the flows going up, and the blues tell us about the flow going down. Looking at the flow vectors, think of the wind in your weather report. We see upward motion in the center of the cell. The material then reaches the surface and starts to move outwards, and it begins to cool and descend. And around 10,000 kilometers below the surface, the material turns back to the center to rise again, and this makes like a cell-like structure. Let's see it in action. We put a heap of corks in our flow field and watch what happens to them. As you see, the corks are being pushed around, and they follow the cell-like flows of the supergranules. They move up to the surface, move outwards, sink, and then get drawn back in again. So this is the supergranule below the surface, and this is how we use sound waves to see below the surface. Thank you all for watching. You can check out more in our paper in Nature Astronomy, or you can check out the cool work we do at the Center for Astrophysics and Space Science at New York University, Abu Dhabi. See you next time.